Thank you for the introduction. So today I will speak about diesel and fuel probe vehicles noise emission assessment as a function of speed, year, and a revolution per minute. I will start from by a brief introduction on the thematic, then I will pass to the research gaps found in the literature, then to our research objectives, the methodology that we follow, the result, and I will conclude with the conclusions. Road traffic noise is a very important problem in Europe. In fact, it was assessed that more than 113 million people are exposed to day, evening, night noise level above 55 decibel A. And on the other hand, more than 55 million people are exposed to night noise level exceeding 50 decibel A. The noise pollution caused several problems, in particularly several health problems such as annoyance, sleep disorders, hearing problems, heart complication, and recently it was assessed that more than 1.6 million of disability adjusted life years were lost in Europe because of problems caused by noise exposure. Therefore, try to assess and to forecast noise levels, and in our case, road traffic noise levels. It's very, it's very important. And in the last decades, research focused on road traffic noise model that can be divided into two main categories. On the one hand, we have statistical models that are based on regression. Basically, they take in inputs the traffic volumes of light duty vehicles together with the percentage of heavy duty vehicles in the traffic flow, and they give us as output the equivalent noise levels. On the other hand, we have more advanced models called dynamics models that can be seen as an union between the noise emission models and the sound propagation models. A noise emission models gives us information on the sound power level of the source, in this case of vehicles. Basically, they take in input information regarding the category and the speed, and gives us the information in terms of sound power level of the vehicle, of a vehicle. On the other hand, the sound propagation model uses the information of the NAMs together with the source receiver distance, the atmospheric divergence, the ground reflection, the building reflection, and the temporal correction in order to provide the lag related to the traffic flow. Uh, However, there are still some research gaps. Particularly, no noise emission model provide a deep characterization of vehicles emission based on motorization. And with motorization, I mean diesel, gasoline, hybrid, electric, LPG vehicles. No extensive studies on vehicle noise emission based on the engaged gear were presented in the literature, and the scarce attention was reserved for vehicles noise emission at the exhaust, basically in idling condition when the vehicles is stopped in neutral gear but the engine is on. Therefore, we would like to fulfill these gaps by developing a noise emission curves. A noise emission curve is the relationship between the sound power level and the speed based on motorization. To provide the noise emission curves based on the engaged gear, it's just for manual transmission vehicles, and to provide a mathematical relationship between the sound pressure level and the engine revolution per minute for the characterization of the vehicle noise emission at the exhaust. So we used two probe vehicles, one diesel powered and another fuel, gasoline and LPG powered, with different weights and engine size, and we equipped them with an onboard diagnostic system in order to extract data in terms of speed, position, and engine revolution per minute. And we conducted several single pass-by tests on a track located in Battipaglia in the south of Italy. And now I would like to speak a little bit deeper about the statistical pass-by test. The pass-by statistical pass-by tests were conducted to obtain the noise emission curves. They are based on the standard 11819 and basically a probe vehicle is driven on a track uh, in absence of other noise sources, and at the same time a sound level meter is placed at 7.5 meter from the central axis of the track at a height of 1.2 meters. The driver needs to maintain a constant speed at least 10 meters before and after the sound level meter. And if during the test the peak in terms of maximum sound pressure level is at least 10 decibel higher than the background noise, then the test is valid and we can estimate the sound power level through the sound propagation formula. Here in the first equation, I reported the sound propagation formula. So basically, by knowing the distance between the receiver and the source, in our case 7.5 meters, and by knowing the LIF max recorded during the test, we are able to estimate the sound power level. And the end of the data collection, we have a data set composed by speed values and sound power level values that we can fit through a nonlinear regression. We need to find the coefficient A, B, C, and D by minimizing the sum of the square errors. And in this case, the coefficient A, B are related to the engine noise contribution that linearly depend on the vehicle speed, while C and D are related to the rolling noise contribution. With the rolling noise contribution, I mean the interaction between tires and road surface, and this part depends logarithmically on the vehicle speed. Then, in order to characterize the sound emission, the noise emission in idling conditions, we perform an ad hoc data collection by placing a sound level meter at 0.5 meters from the tailpipe of the exhaust tailpipe of the car, by forming an angle of 45 degrees from the longitudinal axis of the vehicle. And basically we equipped with the vehicle with an onboard diagnostic system, and the driver inserted the neutral gear and started increasing the revolution per minute by acting on the throttle pedal. And we recorded the sound power, the sound pressure level with the sound level meter. Of course, the clock of the smartphone that was connected with the OBD and the clock of the sound level meter were synchronized. In the end, we have a data set in terms of RPM and sound pressure level that we can analyze, and we can fit the data using this linear regression. We need to find the coefficient A, B. As for the results, here I reported the noise emission curves coming from the statistical pass-by test, both for the diesel vehicle and the fuel vehicle. We obtain good regression, as we can see from the determination coefficients that are above 0.95. And for the fuel vehicles, we can notice that there is a certain dispersion of the measured values, mostly at low speed. And this can be basically due to two things that happen during the data collection. or there was an incorrect lateral distance maintained during the data collection by the drivers, or this is due the effects of the engaged gear that can strongly influence the measured data in this speed range. In order to verify the two hypotheses, we first conduct an analysis of distances. Basically, we re-estimate the sun power level by assuming a source receiver distance of 6.5 and 8.5 meters in order to create a confidence interval. We fitted again the data, and we can see that for the diesel vehicle, almost all the points are in this region, while for the bifuel vehicles, we have quite the same, but the points mostly at low speed are out of this confident region. But we can say that the tests were conducted properly from the drivers, and indeed by conducting a further analysis we noticed that if we fit the data at low speed by using a linear regression and dividing the data set between the runs performed in first gear and the data performed in second gear, we obtain a very good regression, and we can explain this variability, this dispersion of measured point at low speed by assuming that there was an influence of the engaged gear. Finally, here I'm presenting the result related to the noise exhaust emissions. As you can see, the sound power level at 0.5 meter from the exhaust system linearly depend on the revolution per minute. This is basically due to the fact that this type of emission depend on the engine operation, and usually there is a linear relationship between the noise and internal engine variables. We obtain a regression with a high determination coefficient. Please note that in the case of the bifuel vehicles, we repeated the data collection by powering the vehicles with gasoline and with LPG. And in this case, we can note in this graph a certain variability in terms of noise emission when the vehicles is powered in with a type of fuels and with another one. So, to conclude, noise emission curves based on vehicles motorization were provided, and they can be incorporated in the framework of a noise emission model. Noise emission at low speed, below 30 kilometers per hour, depend on the engaged gear for the vehicles that are equipped with a manual transmission, and the vehicle noise emission at the exhaust pipe were obtained through a relationship that bounds the sound pressure level at 0.5 meter with the engine revolution per minute. Um, so I would like to acknowledge the support of these following projects, and thank you so much for your attention. So please let me know if you have any questions.